grounding conductor should be sized appropriately, with the number 10 AWG wire being a common and acceptable choice for satellite dish grounding. The grounding conductor must be as short as physically possible. While there isn't a specific, codified distance limitation for the length of the grounding conductor relative to its size, minimizing its length is crucial for effective grounding. A shorter, straighter path offers lower impedance, facilitating quicker dissipation of fault currents. It's generally recommended to keep the grounding conductor length under 20 feet, but always prioritize the shortest, most direct route practicable. Utilizing the building's existing grounding system is a preferred approach whenever feasible. This method is often the simplest and most effective, as it ties the satellite dish's grounding system directly into the building's established earth ground. To use the building's grounding system, ensure a solid connection to a non-grounding electrode conductor, such as the one connected to the main service panel. If using the building ground, confirm that the grounding system is compliant with local electrical codes and adequately sized for the entire electrical load, including the satellite dish. When the building's grounding system is inaccessible or unsuitable, installing a dedicated grounding electrode becomes necessary. This involves driving a ground rod into the earth to create a localized grounding point. A typical ground rod is at least 8 feet in length. It needs to be driven into the ground so that a minimum of 2 feet of it is in contact with the earth. The depth ensures consistent contact with the surrounding soil, even during dry periods. Copper or copper-clad steel ground rods are commonly used due to their excellent conductivity and resistance to corrosion. Once the grounding electrode is installed, securely connect the grounding conductor from the satellite dish to the ground rod using a suitable grounding clamp or connector. This connection should be mechanically sound and corrosion resistant. It's also crucial to bond all metallic parts of the satellite dish assembly together. This includes the mounting bracket, the dish itself, and any associated hardware. Bonding ensures that all metallic components are at the same electrical potential, minimizing the risk of electrical shock or arcing. Use bonding jumpers typically made of copper wire to connect these metallic parts. Ensure that the bonding jumpers are securely attached using appropriate connectors. Electrical codes, such as the National Electrical Code, or NEC, provide guidelines for grounding and bonding electrical systems. While the NEC doesn't specifically address satellite dishes, its general principles of grounding and bonding are applicable. Consult NEC Article 810 for guidelines on radio and television equipment, which can offer insights into grounding satellite dishes. Local electrical codes and regulations may also have specific requirements for grounding satellite dishes. Always consult with the local authorities or a qualified electrical inspector to ensure compliance. Consider the soil conditions at the installation site. Soil resistivity can significantly impact the effectiveness of the grounding system. High soil resistivity can hinder the dissipation of fault currents. If the soil resistivity is high, consider using multiple ground rods spaced at least 6 feet apart to improve the grounding system's performance. Soil testing can provide accurate measurements of soil resistivity. Grounding systems should be inspected periodically to ensure their integrity. Check for loose connections, corrosion, and damage to the grounding conductors and electrodes. Repair or replace any damaged components promptly. Regular inspections help maintain the effectiveness of the grounding system over time. Proper grounding is essential for protecting both equipment and people from electrical hazards. A well-grounded satellite dish can prevent electrical shocks, equipment damage, and interference with other electronic devices. Understanding grounding principles and following best practices ensures a safe and reliable installation. Additional information is available in IEEE Standard C2 2002 Standard for Safety in Satellite Communications Systems, and also TIA EIA 758B Standard for Satellite Earth Station Antenna Systems. Firstly, always disconnect the power supply to the satellite dish before commencing any grounding or bonding work. This prevents accidental electrical shock. Secondly, wear appropriate personal protective equipment, including gloves and safety glasses, to protect yourself from electrical hazards and physical injuries. Thirdly, use properly insulated tools to avoid accidental contact with live electrical circuits. Fourthly, never work on electrical systems during wet or stormy weather. Lightning can pose a significant risk of electrical shock. Fifthly, if you are not comfortable working with electrical systems, seek assistance from a qualified electrician. Electricity can be dangerous, and it's always best to err on the side of caution. Sixthly, document the grounding and bonding procedures followed during the installation. This documentation can be helpful for future inspections and maintenance. Seventhly, label the grounding conductor and electrode to identify them as part of the satellite dish grounding system. This helps prevent accidental disconnection or modification. Eighthly, use corrosion-resistant materials for all grounding and bonding connections. This ensures the long-term reliability of the system. Ninthly, ensure that the grounding conductor is protected from physical damage. Route it in a way that minimizes the risk of being cut, crushed, or otherwise damaged. Tenthly, regularly inspect the grounding system for any signs of wear or deterioration. Address any issues promptly to maintain the effectiveness of the system. Firstly, a single ground rod may not always provide adequate grounding, especially in areas with high soil resistivity. In such cases, consider installing multiple ground rods connected in parallel to reduce the overall resistance to ground. Secondly, the distance between ground rods should be at least equal to the length of the rods themselves, typically 8 feet. This spacing helps to minimize the overlap of their effective grounding zones. Thirdly, when using multiple ground rods, connect them with a solid copper conductor of appropriate size, such as number 6 AWG or larger. This ensures a low impedance path for fault currents. Fourthly, an alternative to ground rods is to use a ground plate or ground grid. These options may be more suitable in rocky or shallow soil conditions where driving ground rods is difficult. Fifthly, a ground plate is a flat metal plate buried horizontally in the ground. A ground grid is a network of interconnected conductors buried in the ground. Sixthly, both ground plates and ground grids provide a larger surface area for contact with the soil, which can improve grounding effectiveness. Seventhly, the size and configuration of the ground plate or ground grid should be determined based on the specific soil conditions and grounding requirements. Eighthly, consult with a qualified electrical engineer to design a suitable grounding system for challenging soil conditions. Ninthly, the building's metal water pipe can sometimes be used as a grounding electrode, but this is subject to specific requirements and limitations in the electrical code. Tenthly, the water pipe must be metallic and in direct contact with the earth for at least 10 feet to qualify as a grounding electrode. Firstly, the water pipe must also be electrically continuous, without any insulating sections or couplings. Secondly, if using a water pipe as a grounding electrode, it must be supplemented by an additional grounding electrode, such as a ground rod or ground plate. Thirdly, this is to ensure redundancy and provide a more reliable grounding path. Fourthly, the connection to the water pipe must be made within 5 feet of its point of entry into the building. Fifthly, avoid making the connection near any joints or fittings that could compromise the electrical continuity of the pipe. Sixthly, before using a water pipe as a grounding electrode, consult with the local water utility to ensure that it is permissible and that there are no restrictions. Seventhly, gas pipes should never be used as grounding electrodes, as this can create a dangerous explosion hazard. Eighthly, structural steel can also be used as a grounding electrode in some cases. Ninthly, the steel structure must be effectively grounded to the earth through its foundation. Tenthly, the connection to the structural steel must be made with a suitable bonding conductor and connector. Firstly, the size of the grounding conductor should be selected based on the size of the service entrance conductors or the overcurrent protection device for the circuit. Secondly, the electrical code provides tables that specify the minimum size of the grounding conductor based on these factors. Thirdly, when in doubt, it is always best to err on the side of caution and use a larger grounding conductor than required. Fourthly, the grounding conductor should be installed in a manner that protects it from physical damage. Fifthly, it should be routed along a protected path and secured to prevent it from being accidentally cut or damaged. Sixthly, the grounding conductor should be connected to the grounding electrode with a listed connector that is suitable for direct burial. Seventhly, the connector should be made of corrosion-resistant material and designed to provide a reliable electrical connection. Eighthly, the grounding electrode should be located as close as possible to the service entrance or the equipment being grounded. Ninthly, this minimizes the length of the grounding conductor and reduces impedance. Tenthly, the grounding electrode should be accessible for inspection and testing. It should not be buried or concealed in a way that makes it difficult to access. Firstly, the grounding system should be tested periodically to verify its effectiveness. Secondly, a ground resistance meter can be used to measure the resistance of the grounding system. Thirdly, the resistance should be as low as possible, ideally less than 25 ohms. Fourthly, if the resistance is too high, additional grounding electrodes may be required. Fifthly, the grounding system should be inspected visually for any signs of corrosion, damage, or loose connections. Sixthly, any issues should be addressed promptly to maintain the integrity of the grounding system. Seventhly, the grounding system should be documented, including the location of the grounding electrodes, the size and type of grounding conductors, and the results of any testing. Eighthly, this documentation can be helpful for future inspections and maintenance. Ninthly, the grounding system should be designed and installed in accordance with all applicable codes and regulations. Tenthly, consult with a qualified electrical engineer or electrician to ensure that the grounding system meets all requirements. Firstly, surge protection devices can be used to protect sensitive electronic equipment from voltage surges. Secondly, these devices should be installed at the service entrance and at the equipment being protected. Thirdly, surge protection devices work by diverting excess voltage to ground, preventing it from reaching the equipment. Fourthly, surge protection devices should be properly grounded to function effectively. Fifthly, lightning protection systems can be used to protect buildings from lightning strikes. Sixthly, these systems consist of air terminals, grounding conductors, and grounding electrodes. Seventhly, lightning protection systems work by providing a low impedance path for lightning current to flow to ground, preventing damage to the building and its contents. Eighthly, lightning protection systems should be designed and installed by qualified professionals. Ninthly, the grounding system is an essential part of the overall electrical safety system. Tenthly, a properly designed and installed grounding system can protect people and equipment from electrical hazards.